All right. I smile because a lot of these slides are like, actually we covered in Chemistry 1, General Chemistry 1, when we were talking about atoms being bonded together. So we talked about, see if this reminds you, atom A bonds to atom B. And remember, there's a tug of war with regard to that dash right there is a pair of electrons either being shared or transferred. It's a tug of war. And it results in what we call a polarity of that chemical bond. So we're going to talk about bond polarity, and then we're going to scale it up, because if you have, for instance, A bonded to B, bonded to C, bonded to D, okay, that could be a molecule, okay? And is that molecule, what kind of polarity does that molecule bring? So we have bond polarity and we have molecular polarity. Those are two different things. Try to convince you of that. So I'll go ahead and draw the A and the B again. Atom A bonded to atom B, right? Okay. We said that if those electrons are shared, 2 electrons, if they're shared, okay, we call that a covalent bond. They're stuck together. Those 2 atoms are stuck together with a chemical bond called a covalent bond. A pair of electrons are shared. That works. In contrast to, check this out, atom A and atom B. Let's go ahead and make atom A the metal. It's going to transfer an electron or electrons, and it's going to become a cation, and B is going to be an anion. Is that kind of ringing a bell there? And dot, 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 dot. I'll go ahead and grab my purple. This right here is an ionic bond. Okay, that is an ionic chemical bond. Example of an ionic chemical bond is sodium chloride, NaCl. An example of a covalent bond is, I think we usually pick on water. An oxygen with 2 hydrogens skipping off, those bonds are covalent. Na dot 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 Cl. I'll go ahead and just for kicks, I'll put a plus where the Na and I'll put a minus with the Cl. Okay? All right. Covalent bonds, electrons are shared. Okay. Oops. I missed something. Okay. So electronegativities, like I said, this is just to kind of get the cobwebs out. Electronegativity, remember that's the symbol chi, like the X with the fancy, that's electronegativity, okay? So we said like if atom A and atom B have similar chi values, electronegativity of A, electronegativity of B, okay, if they're similar, then electrons are going to be shared. And actually, I'll go ahead and finish this thought. We said, and you're going to see the electronegativity values of the elements again, we said you can come up with something called a delta chi. Remember that? It's the absolute value of the electronegativity, differences of electronegativities. So, in italics there, it says another thing that we talked about probably in your high school chemistry days. Remember, if you take, this is my P block, okay, this is P block, this is S block, and this is, D block? And down here, that's F block, okay? Actually, there's a jag here. You know where I'm going with this, don't you? Okay, good. So these right here are your nonmetals. And what it says in italics is it works out really well. You can pick a pair of nonmetals, put a bond between them, and probably that bond's going to be covalent. If you take a nonmetal and a metal, that bond between them is probably going to be ionic. So covalent bonds. Electronegativity, the symbol, the Greek letter chi. By definition, electronegativity is basically an atom that's bonded to another atom, and the tendency for the atom to like hoard electrons to itself. So that's why I call it a tug of war. That's the hoarding kind of tug of war. We say if something has a high electronegativity value, chi value, that means it's going to hoard electrons to itself. And remember, there is this trend right here with the purple arrows for the trend of electronegativity values. So electronegativity increases as you go to the right, and electronegativity increases as you go up. So it's like a... And see, it's like we've seen all these slides before. Remember this one? But if that one's harder to tell, this is my favorite one. In fact, I went ahead, and you might want to also. There will be problems that you're going to have to kind of figure out looking at compound, and these values might come in handy. So I know yours is really small. Yeah, okay, it's like blending in. But, do you guys want one of these? Maybe? Sure. Okay. Actually, I'll print out one for everybody, because it really comes in handy. So those are the electronegativity values. So this slide you see in your notes, actually like 3 slides from now. But I kind of wanted to remind you of what this delta chi is. Remember, delta chi, or electronegativity difference, is basically you have the Pauling value of the 2 atoms to evaluate basically the bond between them. So the chemical bond between them is going to fall into one of these categories, okay? Those first 4 categories are all examples of a covalent bond, electron share. And I think I mentioned in Gen Chem 1 that when does an electron go ahead and be transferred because the electronegativity difference is so high? About 1.7, and that actually is debatable, okay? So electron can be shared, but it's not necessarily shared equally. So here's where, let's go ahead and pick on water, and I think we may have done this one before too. Let's go ahead and draw our oxygen atom, covalent bond hydrogen, covalent bond hydrogen, and let's kind of evaluate these, which I guess they'd be the same, wouldn't they, because they're symmetrical. Let's go ahead and do an evaluation of that one on the left. So if we wanted to evaluate that bond, okay, we would look up oxygen, and this is where, like I said, I'll get you a big one of these. We could look up the electronegativity of oxygen is 3.5. The electronegativity of hydrogen is 2.1. Okay, so the electronegativity difference for that covalent bond, delta chi, is absolute value of 3.5 minus 2.1, 1.4? Yes. Okay. 1.4 falls right kind of between those two, doesn't it? 1.4. So this is where we would say that bond between the oxygen and the hydrogen, actually both of those bonds, and the other oxygen and hydrogen bond, it's very polar. And here in a minute, we're going to go ahead and use the convention we used before. So the oxygen's 3.5, it's more electronegative. So it hoards electrons to itself more. So we would tend to think that this is what, kind of negative-ish, because it's got more electrons. But instead of doing a full negative, we use the symbol for partially. Okay, partial. It looks kind of, it's actually a lowercase delta. It's like an S with a little loop. That's partial. So we say that that oxygen's partially negative. And in the tug of war, those hydrogens are missing out on the battle for electrons. So they are partially positive. Partially positive. So when we talk about the polarity of a bond, we have just talked about the polarity of the left oxygen-hydrogen bond and the polarity of the right oxygen-hydrogen bond. So there's both bonds are polar. But I'm going to warn you that it's possible to have kind of a similar situation with a different molecule, to have two polar bonds and kind of their polarities cancel each other out. I'll try to prove this to you. Won't probably till Friday, but their polarities of the individual bonds cancel each other out, so the molecule is non-polar. It's kind of a cool thing. Okay, as it turns out, water is polar just because of its shape. But that is bond polarity. All right. So when electrons are shared between atom A and atom B exactly equally, okay, we call that a perfectly covalent bond, or a non-polar covalent bond. Makes sense. But the only way that's going to happen is their chi values are the same. If delta chi is equal to 0, that's it. So a good thing, or a good obvious time when their electronegativity values are the same is, check this out, if they're the same element. Like, duh, right? But we talked about some elements like to be diatomic. Remember the Hofbräunickel? The oops, this should be a H. Hofbräunickel. Are there 7? 1, 2, 3, 4, 5, 6, 7. Okay, so I put little 2s down there because they like to run around as diatomic. And in each of those cases, the electrons are shared totally equally between each atoms. Okay, so we have a non-polar covalent bond, and then we have kind of these degrees of polarity, okay, because you had something that was a little slightly polar, something that's polar, and something that's highly polar, right? So the degree of polarity actually can change depending upon increasing difference in electronegativities. Notice that if we're talking about, if somebody says, if somebody identifies a bond as being covalent, electrons have to be shared, okay? Only if delta chi is generally greater than 1.7 do our electrons transfer. All right, so this is the same one that I kind of brought in earlier. So we have a degree of polarity. We would say that here this is increasing polarity. I'll say bond is increasing polarity. And really, like I said, part of the task here in this first unit ultimately is going to be evaluate molecules. And the way you would evaluate a molecule is to kind of go bond by bond in some cases. Sometimes it's polar, sometimes it's really polar, sometimes it's just a little bit polar. So degree of polarity, and it ends up actually being a math thing. I'll kind of show you. It might not be until Friday. So here we have Cl2, HCl, and NaCl. And if you were to come up with, for this first one, electronegativity difference between those two chlorine atoms is 0, right? We could evaluate the delta chi. Okay, electronegativity difference for this one, and this is where you go back. It's that 2.1 minus 3.0. I got 0.9 for HCl. And for NaCl, I got 0.9 minus, again, 3.0. I got 2.1. Okay, so that's kind of what we're talking about. Okay, so I kind of already showed you this a little bit, But carbon monoxide, now this isn't the final Lewis structure of carbon monoxide, because you're like, dude, where's the 8 electrons around the carbon and the oxygen? But just kind of a simple structure showing the arrangement. Now, if you find, even without this, if you find carbon and oxygen on the periodic table, notice they're in the same period, but oxygen is to the right, so it would be a higher electronegativity value, right? So that's why actually, even without these really values, just a regular periodic table, we could go ahead and show oxygen is partially negative and carbon is partially positive. Okay, for carbon monoxide. Again, not the final Lewis structure, but just kind of showing you where the kind of electron cloud is mostly over the oxygen. I think it's a triple bond. Anyway. So this whole, this thing down here is kind of, if you've done much with physics, you know that actually they work with vectors a lot. Vectors show both magnitude and direction. So here we have an arrow. This arrow starts here, and this arrow ends here. Okay, where it starts is partially positive, where it ends is partially negative, and the length of the arrow gives magnitude. Because I mentioned sometimes, you know, if your delta chi is higher, that arrow is going to be longer. And if your delta chi is, if your electronegativity difference is not very great, then that, literally that arrow will be small. Or the length of that arrow will be less. So like in physics, a lot of times when they combine forces, if they're careful about orientation, you can take this force plus this force plus this force and draw what we call a resultant force kind of between them, all of them. So, okay. So this is kind of neat, and I think we talked about these before. They're potential maps where the red indicates hot for electrons. Okay, negative extremes, so this would be your partially negative, and anything that's blue would be electron deficient, so it would be partially positive. So notice with the chlorine molecule, you know, Cl combined with attached to another chlorine atom, it's perfectly covalent, so it's neutral. Electrons are totally shared just fine with both of them. Okay, if we go into HCl, now this is where you're like, well, who's going to get more electrons, the hydrogen or the chlorine? Well, again, you have to look at the periodic table, and even though, remember, hydrogen on my periodic tables appears twice, appears over here and also over here. Actually, chlorine is more electronegative than hydrogen. Hydrogen 2.1, chlorine 3.0. So you can't really tell it much, but the chlorine looks a little redder. Just a little redder. And here we have where an electron is entirely transferred from the metal, from the sodium to the chlorine. So H2, hydrogen, is another diatomic element. So a hydrogen molecule would look like this. It'd be nonpolar. That covalent bond is nonpolar, so it's a nonpolar covalent bond. HF, fluorine is 4.0. Oh my gosh. Well, fluorine is above chlorine, so that makes sense. So if you take 4.0 minus 2.1, you get 1.9. So definitely electron is transferred from the hydrogen to the fluorine. Or they're showing it as a covalent. Well, I don't know. See, that's where I got in trouble. Did you guys just see that? They're showing this as actually covalent. And when I come up with this electronegativity difference, one is 4.0. Oops. Oops, my pen's not working. Is that what you guys get too? Okay, good. So according to my little list, that would be an ionic bond, but they're calling it a very polar covalent bond. Welcome to my world. No, I'm just kidding. So are you wondering what do you do in those cases? Well, I'll tell you, in the context of this course, it's not gonna throw you a curve, but it is good to know that it's out there. That kind of ionic electron transferred, the threshold being electronegativity difference of 1.7 in this case. But if we go down here, let's see, lithium 1.0, fluorine again 4.0. Yeah. Well, yeah, right. Electronegativity difference of 3. Electrons transferred from the metal to the non-metal. Okay. So all that we've been talking about, the electronegativity differences, between atom A and atom B that's bonded together. We're just isolating a particular chemical bond and evaluating its polarity. That's bond polarity. Okay? And I think yeah. So on Friday, we're going to take it up a notch and basically look at a molecule. You're like, well, what's a molecule? Well, it's at least 2 atoms or more that have maybe multiple bonds. And how does the polarity of the molecule wash out? Okay, and like I've been alluding to, it's basically, at one level, you need to actually kind of look at the individual polarity of the bonds and kind of look at it holistically, is what, if the molecule is polar or not. So, but I think what I've done in the past, I'm going to do it again, is I'm going to just stop there so we kind of separate the two a little bit. So, I'll let you out a little early and we'll pick up there on Friday.